Well, good morning, everybody. Today what we're going to do is we are going to continue a conversation that we started last time in lab when we did the pH indicators lab. So you may remember as we were introducing the idea of the lab, we talked about some general ideas about what acids do, what bases do, kind of about what pH is. You spoke to a couple of these questions in the conclusions for the lab that you just turned in. So guys, what we're going to do today is we're actually going to continue this conversation. And in order to continue the conversation, we've got to make sure that we are all fundamentally in the same place. So you don't have this slide in front of you, but as a result of what we did last time in lab, we should all be able to agree on these fundamental ideas. So from the experiences that you had last time, you should understand that acids generate lots of hydrogen ion. The more they make, the stronger the acid. We also talked about the idea that bases create OH, and the more base an acid, or the more OH a base creates, the more basic that substance will be. In addition to that, we talked about the idea that water has equal amounts of H and OH. Bringing H and OH together, obviously we get H2O, and so that makes sense. We talked about the idea that the pH of water is 7, which is right in the middle of the 1 to 14 pH scale, and these ideas start to link together. In addition to that, you should be comfortable with the idea that the pH scale is a scale that we use to measure the strengths of acids and bases. As we remember, it does range from 1 to 14, and then we remember that the pH scale is a logarithmic scale, meaning that it moves by powers of 10. So the low numbers on the pH scale, 1 through 7, are the acids. Smaller the number, the stronger the acid. At 7, water, we consider that neutral, and then above 7 to 14, we understand that those things are basic, but we understand that every time the pH scale moves by a factor of 1, the strength of that acid or base changes by a power of 10. So this is where you should be right now as a foundation. This is the reason we did the lab last time. And from there, we're ready to move on and talk about what we're going to do today. And this is where things pick up in your notes. So today, guys, we've actually got 4 things that we're going to accomplish. First of all, we're going to figure out what an acid and a base is. Now you're going, wait, we already know acids give away hydrogen, bases give away OH. And while that's true, it's not the entire story. So we are actually going to look at 2 different definitions for acids and bases. Then following that, we're going to talk about how acids and bases react. You're going to find out in just a minute that based upon these 2 definitions, there's actually 2 different ways of understanding the way acids and bases react, and we'll look at those one at a time. Then, as we move through this, we need to talk about what do acids and bases form when they react, and that'll tie back to their reactions, and then that will also tie back to the 2 definitions. And then the final thing we're going to do today is maybe ask a question that you've been curious about since the lab. Why is it that stronger acids have lower pHs? And then as we get up into the larger numbers than 7, they're not acidic, they become basic. So this is actually what we're going to accomplish today. And to begin this, what we need to do is we need to lay out some fundamental ideas about what does it mean to be an acid and what does it mean to be a base. And so what I like to do is I like to start the conversation by creating some common understandings about what things are acidic. So guys, when we talk about things that are acidic, typically my students will go, oh, I know that there's acid inside of car batteries. What kind of acid is it? Well, it's battery acid. Yeah, kinda. Guys, it turns out the battery acid is actually sulfuric acid. It's H2SO4. And you'll notice that in H2SO4, there's actually 2 hydrogens that actually makes this an especially acidic substance. Then guys, after that, I believe that most of you understand that your stomach is a bag of acid. Specifically, it's hydrochloric acid, and that acid is actually in a very similar concentration to the hydrochloric acid that we used during the percent yield lab. Not the lab that we just did with dilutions, but the percent yield lab, that acid is pretty close to the acid that's in our stomachs. You may be wondering, why does that not then burn our stomachs? And the answer is because our stomachs have a lining, actually made of mucus, that keeps the acid from actually touching the flesh, if you will, of our stomachs. If you get a hole in that lining, you end up with what's called an ulcer, as that acid does in fact burn the stuff of our stomach. Then we have maybe one that you did know is an acid. This is vinegar. Vinegar is actually acetic acid. It's the acetate ion plus a hydrogen. And then, guys, many of you are aware that there's a whole class of fruits called the citric fruits, the citrus fruits, and they all contain citric acid, which has a chemical formula of this. Okay, so where does this then leave us with 4 examples in terms of what things are acidic? Well, maybe you're noticing the thing they all have in common. And the thing that all of these substances have in common is the presence of hydrogen. That, of course, ties back to what we already understand about acids producing or releasing hydrogen, and this all makes sense. This is where the conversation gets a little fuzzier. Because typically when I turn to a group of students and say, okay, guys, let's now talk about bases, typically the only base that people can think of, if they were paying attention, is oven cleaner, because last time in class we talked about oven cleaner being a base, or maybe you remember sodium hydroxide was the base that we used in lab. Well, it turns out those two things are the same. Oven cleaner is sodium hydroxide, and it has this formula. So now let's push a little harder and see if we can think of other things that are basic. So another substance that it makes sense as a base is actually Rolaids. We take Rolaids when our stomach feels acidic, and the base in Rolaids neutralizes the acid and it keeps our stomach from hurting. Guys, Rolaids is actually aluminum hydroxide. The reason that we use aluminum hydroxide is because it actually contains 3 OHs. This makes it an especially good base because for every formula unit of aluminum hydroxide, you get 3 hydroxides. So there's another example of a base. Notice that both of these substances contain OH, and that makes good sense relative to what we know about bases. This is where things get a little fuzzier. Guys, ammonia, which is NH3, you can see that on the cartoon bottle or down below. Guys, NH3 or ammonia is a base, but you'll notice it doesn't contain any OH. Another example would be sidewalk chalk. Sidewalk chalk, which is calcium carbonate, is also basic, but it does not contain any OH. This then is where we need to start talking about our 2 definitions for acids and bases. Because, guys, you'll notice that as we look at the screen, all of these things fit neatly into our understanding of acids and bases. But what about things like NH3 and chalk, calcium carbonate? Well, guys, that is the reason we need another definition for acids and bases. So, if I can get my board to go, nope, not going to work. This is going to freak out for a second, but we're okay. We're going to click here, and then we're going to go back, and then we're going to clean this up. This then brings us to our definitions for acids and bases. You'll notice on the next page in your notes, this is there. And the first definition for acids and bases is the Arrhenius definition for acids and bases. This was about 1870, maybe 150 years ago, a guy named Arrhenius was studying acids and bases, and he said this. He said that acids are substances that release hydrogen ion. And you're saying to yourself, yep, already knew that. It's because the definition we talked about last time was the Arrhenius definition for acids and bases. You'll notice that there's a blank in your notes. It's also underlined up on the screen, and that gives you the chance to fill in your notes with the idea that in the Arrhenius definition, acids release hydrogen ions. So if you understand that, you can probably fill in the next line in your notes, because bases then release, as we said earlier, OH. So acids release hydrogen ions, bases release OH ions, and this then leads us to what we call the general reaction for Arrhenius acids and bases. And it goes like this. When acids and bases react, we end up with salt, and we end up with water. Now, guys, be careful when you think about salt. That is not just NaCl. Remember, we talked about the idea for months and months that salts are a metal and a nonmetal ionically bonded together. The nonmetal, small and strong, steals electrons from the metal, big and weak, and we end up with ions that attract, crystals, everything we know about salt. So with that said, let's take a look at an example reaction. So here we have HCl and we have aluminum hydroxide. Now you'll notice that you've also got this in your notes, so this will be easy to follow along. So looking at this and seeing that we have two compounds reacting together, perhaps you see that this is going to be a double displacement reaction. The positive hydrogen will hook up with the negative OH, and then the positive aluminum will hook up with the negative chloride. Now, given what you understand from taking the previous test, hydrogen is +1, OH is -1. That means that one of our products is water, H2O, or you can think about this as HOH. And then looking at our other product, which is the salt, we understand that aluminum is +3, chlorine is -1, and as a result, our salt is, it's not going to switch. Come on, buddy. Nope, not going to go. All right, let me clean this up and then we'll do it this way. So guys, our salt will then be aluminum chloride. Now, we're not going to spend the time to balance this. You easily could, but it's not the point. What you do need to see is that we have an acid that contains hydrogen and a base that contains hydroxide, and we get out water and we get out a salt. That is the general reaction for an Arrhenius acid-base reaction. Now, guys, moving along from here, this brings us to an interesting idea. This gets us back to our previous slide where we can now talk again about the things that are acids and bases. And so we have this understanding that acids contain hydrogen, and that's the case, and some bases contain OH. Well, what about these bases down here that do not contain OH? How do we explain that? That then leads us to the work of another set of scientists. These guys actually didn't work together, but they did the same work, so they both get credit. Their names are Bronsted and Lowry. And Bronsted and Lowry tackled this idea of how do we understand bases that don't contain OH. So here's what they did. They said, okay, what is an acid? Well, we're going to change the terminology a little bit. An acid is a proton donor. So acids give away protons. Now guys, if we pause for a second, allowing you time to look up at the previous slide and looking at the definition under the Arrhenius structure for an acid, maybe you see that these are actually the same definitions. If you don't see that, turn your attention to the circle on the right. So guys, let's take, for example, a hydrogen atom. I'd encourage you to fill this in. A hydrogen atom is 1 proton, 0 neutrons, and 1 electron. That is a hydrogen atom. So what do we do if we want to make this hydrogen atom a hydrogen ion, and specifically a positive ion? Well, obviously we're not going to add a proton because then it's helium. So what do we do? Well, in order to do that, to make this positive, we take away the electron and look at what we have left. We have a proton. So it goes like this. Arrhenius said that acids give away hydrogen ions. Bronsted and Lowry said that acids give away protons, but these are the same, and so the definitions are the same. So I would encourage you on your paper to draw a line starting there and going all the way up to the Arrhenius definition of an acid. And I would encourage you to write down the word same next to that, because literally these are the same definitions. See if we can get this to go. No? Okay. So, guys, that's actually the next bullet in the slides, and I know you can see that. But the idea then, if you need, is that this is the same as the Arrhenius definition because hydrogen ions are protons. Okay, so now let's talk about bases because this is where this gets different. Bronsted-Lowry definition of a base, and he said this: bases are proton acceptors. This is where things get different because no longer do you need to give away OH to be a base. You actually have to have the ability to take in protons. And this changes the idea of acids and bases because now acids simply give away protons and bases take in protons. So what does that look like? Well, guys, importantly, it no longer means that we're making water. Water does not have to be a part of the equation anymore because we don't give away OH, so we may not form water. So if that's the case, what do we form? And the answer, as you see in your notes, is conjugates. Now, guys, understand in this class, understanding conjugates is all that you're going to need to do. When you come back for AP next year, we are going to spend weeks talking about the chemistry of conjugates. It's a fascinating topic, and we spend a lot of time on it. All you need to know is what they are. So, where have you heard of the word conjugate before? And if you've taken a foreign language, you probably know that one of the things you learn to do is conjugate verbs. You're taking the form of a verb and you're changing it into a new form of the verb. And so, guys, that's exactly what it means in chemistry as well. Conjugate just means new. So you are forming a new acid and a new base. So how does this work? Well, the answer is this. The conjugate acid is formed when the base gives a proton. Now, when this happens, the base becomes the conjugate acid. But you also need to be careful of charge changes. Because this thing is picking up a proton, its charge goes up by 1, and so the charge of the conjugate acid goes up by 1. Now, what about conjugate bases? Well, conjugate bases are new bases formed when the original acid loses a hydrogen. And when this happens, the acid becomes the conjugate base. And as that acid loses a hydrogen to become the conjugate base, that hydrogen ion is positively charged, and the charge goes down by 1. Okay, so guys, there's a very real chance that as you're filling in these guided notes, you're going, wait a minute, this is a little confusing. Guys, here's what you've got to be able to do. It's on the next slide. For this class, you have got to be, and I mean general chemistry, you have got to simply be able to identify acids and bases and conjugates. So here's how to do it. Go to the next slide and take a look at this sample reaction. This is the process for figuring out acids and bases and conjugates. What you're going to do, and guys, I'm going to do this a little bit out of order. You should start on the left and try this and then try this. I'm going to actually do these out of order. Because you'll see in a second, it actually doing the first one first sort of gives the rest of it away. So what are you going to do? And guys, the answer is this. You are looking for the acid. And again, what do acids do? They give away hydrogens. So guys, we should start with the one on the left, but let's start with water. So if water is an, if water is an acid, it would give away a hydrogen. And if water gives away a hydrogen, what's left is OH. So now what we need to do is look for OH. This isn't OH, this isn't OH. So we know that's not what happened because there is no OH as products. Okay, so now let's try the other one. Let's turn our attention to H2SO4. Now, if H2SO4 is the acid, it would give away a hydrogen. And when it gives away a hydrogen, we are left with HSO4. And sure enough, over there on the right, we've got HSO4. That tells us then that the H2SO4 is in fact our acid. Now guys, here's the deal. Once you know which one is the acid, everything else just flows. Because if this is the acid, then water's got to be the base. One's the acid, one's the base. Now, how do you find the conjugates? And guys, this is the trick. Go to the acid, take away the hydrogen. When you go to the acid and take away the hydrogen, the other thing, it's not letting me draw. The other thing is the conjugate base. Whatever's left over is the conjugate base. So again, to find your conjugates, just go to the acid, take away the hydrogen, whatever's left, by definition, is the conjugate base, and then that makes the other, if this will go, it's not going to go. Come on, baby. No, I got to do it this way. So guys, the other then becomes the conjugate acid. So once again, looking at the left, find the one that loses the hydrogen. That's your acid. The other has to be the base. Then go to the acid, take away the hydrogen. Whatever's left over is your conjugate base. And then the last one left is your conjugate acid. So let's look at another example. Here we have another reaction that is an acid-base reaction, and we're going to try to find our acids, our bases, and our conjugates. So we go to the first substance on the left, we take off a hydrogen, and guys, when you take off hydrogens at the front or the end, not the ones that are in the middle. You don't mess with these. So we take off that hydrogen, and oh my gosh, look at that. There it is on the right. That means that we have found our acid. So we come along and we say, okay, that then makes this, the CH3COOH, that then makes the CH3COOH our acid. And if that's the acid, the other is our conjugate base. Now, in order to figure, not conjugate base, base. Now we need to find our conjugates. So the first is the acid, the next is the base. Now let's find our conjugates. So again, we go to the acid, take away the hydrogen. What's left is this, and that would make this our conjugate base, and then that makes H3O plus our conjugate acid. So let's see if it'll allow me. Nope, not going to do it. We'll go back here. That makes this our conjugate base, and that our conjugate acid. Now guys, this leads us to an interesting point. You'll notice that in both of these examples, on the left we have acids and water is our base. But in both of these examples, our acids give a hydrogen to water. Now guys, there's something here you've got to understand. All acids are substances in water. So anytime you have an acid, you've got this reaction taking place when you create the acid. And acids always do this. They give hydrogens to water, and water turns into this molecule. And guys, this molecule is important. It's actually so important that it has a name. The name of this molecule is the hydronium ion. And guys, hydronium ion actually has the formula H3O plus. But guys, the thing that you've got to understand is that this hydronium ion, this H3O plus, is always formed when an acid is added to water to make the acid. So if you're getting an acid burn and you're like, oh, the acid's burning me, it's actually not. The thing that's burning you is the hydronium ion, because that's all acids do is give hydrogen ions to water, protons, and they form hydronium ion. And it's the hydronium ion that actually does the reacting with the acids. Okay, so we're going to look at one more example of acids and bases and conjugates. This one's a little bit different. It looks like this. So we've got NH3, water, and the products are NH4 plus, which is called ammonium, and then we've got hydroxide. Now, if you're paying close attention, you may remember this, NH3. It's ammonia. And we ask the question, how can ammonia be a base if it doesn't contain any OH? Well, guys, the answer's on the board. Let's find our acids and our bases and our conjugates. So we go to NH3 and we take away a hydrogen and that leaves us with NH2, but we look over on the left and there is not any NH2, so that is not the acid. So now we go over here and we go to the water and we take away a hydrogen from the water and we end up with OH. Sure enough, guys, there's our OH. And this is what Bronsted and Lowry figured out. These substances that are basic but don't have OH in them actually make OH by stealing a hydrogen from water. It was a breakthrough discovery, but this explains how things like chalk and ammonia can be basic if they don't have OH. So where does that leave us? Well, the idea then is this. The water loses a hydrogen, so that makes water our acid. And NH3 is our base. Then, finding our conjugate, we go to the acid, which is H2O, take away a hydrogen, and what's left is our conjugate base, OH, and then ammonium, NH4, not ammonia, but ammonium, NH4 plus, is our conjugate acid. Now, guys, this leads us to another interesting conversation. Did you notice this? In the first two reactions, water is a base, and in the third reaction, it's an acid. So which is it? Is water a base or is water an acid? And of course, the answer is yes. But guys, that property makes water what we call, and there's a line for you to write this down, that makes water what we call amphoteric. Amphoteric refers to a substance that can act as an acid or a base depending on the other substance. And as a matter of fact, that's actually what acid and base means. When we say that a substance is an acid, we mean a more acidic than water. And when we say a substance is a base, we simply mean more basic than water. Again, remember, water is in the middle of the pH scale at pH 7. And if your question then becomes, are there other substances that are amphoteric? The answer is absolutely, and you're going to see some examples of that in your homework assignment today. All right, so guys, we have one more thing to do in order to wrap up the day. We've talked about two definitions for acids and bases. The Arrhenius definition, where acids give away hydrogen ion, bases give away OH. When they react together, they make salt and water. Then we talked about the Bronsted-Lowry definition, where acids give away protons, bases take in those protons, and when they react together, they form a new acid, the conjugate acid, and a new base, the conjugate base. Then as we got into this conversation about acids, bases, and conjugates, we came to the idea of hydronium ion, which is what acids always make when they're mixed into water in order to create the acidic solution, and then amphoteric, which means a substance that can be an acid or a base. Okay, so let's do this for a couple moments. Let's take a second and let's actually practice on these examples. We have examples here of acid-base reactions, and then we have the conjugates on the right. I will pause the video for a moment, and you will have the opportunity to figure out which are your acids, your bases, and your conjugates. And again, guys, this is all you've got to be able to do with acids, bases, and conjugates this year. In AP, we get into the real chemistry of conjugates. And frankly, guys, it's fascinating. You're going to love it if you're coming back. Okay, so now that you've had the opportunity to look through these, let's actually look at the answers. So looking at the top reaction, we have CH3COOH on the left. Notice we have CH3COO on the right. That means that the CH3COOH is our acid. And again, guys, once you know the acid, the rest falls into place. That makes this our base. Then go to the acid, take away the hydrogen. What remains is the conjugate base, and then the other one, in this case the CH4, has to be the conjugate acid. Guys, also notice what happened to the charges. When CH3, the base, picked up a hydrogen, it went from -1 to 0, and then when acetic acid lost the hydrogen, it went from 0 to -1. So the hydrogen changes the charge. The hydrogen ion. The base takes in the hydrogen, its charge goes up. The acid loses the hydrogen, and its charge goes down. Okay, so moving along and looking at the rest of these then, let's move through these and complete the day. Complete this section. On the left, we have CH3OH. On the right, we have CH3O minus. That means the CH3OH is the substance that lost the hydrogen. That makes this the acid, and the other, of course, is the base. Then finding our conjugates, take the hydrogen off, and what we're left with is the conjugate base, and the other is the conjugate acid. Now down here at the bottom, you'll notice in this last one, we have the hydronium ion, the H3O ion, as one of the products. That's kind of a clue that the stuff on the left, the HF, is the acid, because we know that all acids, when they go into water, form hydronium ion. But if you didn't pick up on that, the HF, take the hydrogen off, you're left with just F minus. That's what's on the right. That means that HF is the acid. Water is the base, then our conjugate base is the acid minus the hydrogen, and then our conjugate acid is the hydronium ion, and again, that's the active ingredient, if you will, in acids and bases, or in acids. Okay, so guys, we are now done at some level with acids, bases, and conjugates. We have one more thing that we need to talk about, and that is, why is it that the stronger an acid, the lower the pH? Again, changing pages, you'll notice that you've got some blanks to fill in, and let's talk. So guys, before we said, and this is what you wrote in the conclusions to your lab that you just turned in, we said that pH is a measure of the strength of an acid or base, and that's kind of true, but actually what it is this. It is the measure of an acid's strength focusing on the formation of hydronium ion. So when we measure pH, what we're actually measuring is the concentration of hydronium ion, but we understand that hydronium ion is what is formed when acids go into water. So those ideas kind of match up. So when we talk about hydronium ion, we've got the acid losing a hydrogen ion to water. It forms hydronium ion, and then our conjugate base. And the more hydronium ion that's formed, the stronger the acid. But guys, when we talk about this, what we're actually then talking about is the hydronium ion concentration. The more there is, the more concentrated, the stronger the acid. The less there is, the lower the concentration, the weaker the acid, and then at pH 7, beyond that, it's a base. So it brings up an interesting conversation. Thinking back to what we've learned in previous units, we already have units for concentration. What are they? Not moles, molarity. So guys, we already have a unit for concentration, which is molarity. So why on earth do we use pH when we already have units for concentration, which are molarity? Well, guys, the answer to this question is interesting, and I'd encourage you to not read the notes. I'd encourage you to follow along up on the board. So here's what's going on. Guys, even really, really strong acids, like acids that if you got them on you, you'd be in pain. Guys, even these relatively strong acids have pretty low concentrations of hydronium ion. They're certainly less than 1, and often they're small decimals. So this leads us then to a problem. These small concentrations, these small decimal numbers, are often best represented in scientific notation. But the trick is that even numbers in scientific notation are cumbersome, and this is why we use the pH scale. So guys, join me here at the screen and let's talk. So imagine that we have an acid that has a hydronium ion concentration of 0.001. That's actually pretty darn acidic. Like, you wouldn't want to get that on you. And its molarity is 1,000th of a molarity. Well, that number is kind of a pain to write. So let's put it in scientific notation. So 1 times 10 to the negative third. Well, that number is actually even worse. But it's that number that we need to understand pH. Because if we have a solution with a hydronium ion concentration of 0.001 or 1 times 10 to the negative third in scientific notation, guys, let's then talk about the pH. Because the pH of this substance is 3. So as you're filling in the blank with the number 3, ask yourself this question: where did the 3 come from? And I'll bet you see it. It's right here. Guys, that's all pH is. It is the exponent of the molarity for hydronium ion. It is the molarity in scientific notation, but all we're focusing on is the exponent, and we drop the negative. So get rid of this, and that's where the pH comes from. So for those of you that are more comfortable thinking numerically, you may now beginning to understand why the small numbers are the small numbers are the strong acids. But let's invite everybody into the conversation. And guys, it goes like this. This is a pH scale, not unlike the one that we put up on the screen, but now this pH scale also gives us the molarity. So the molarity, let me zoom out so we can do this. So guys, the way that this works is the molarity is here on top, and the pH is down here at the bottom, and it goes 0 through 14, and then we've got the molarities in essentially what is scientific notation. So as we go, guys, maybe some of these things are interesting to you. I always find it interesting that blood is acidic. I think most people, or I'm sorry, basic. Most people have this idea that it's acidic, and it's not. Your blood is actually basic. Sometimes people are surprised by the fact that milk is acidic. It actually is. Milk is slightly acidic. This one also kind of takes people by surprise. The pH of soda is close to 4. Soda is actually fairly acidic. It used to be that people would actually pour Coke in their radiators to eat the rust out of their radiators. Now there's a lot easier ways to do that. But at any rate, we've got all these interesting pHs. Now what we're going to do is we're going to take these ideas and let's link them together with what they mean relative to molarity. So guys, let's take, for example, stomach acid, the acid in your stomach. Your stomach acid has a pH of 2. So what does that mean? Well, if you take that number and carry it up, guys, that means the molarity of the acid in your stomach is 10 to the negative second. But if you're not familiar with that, that number written out is 0.01 molar. That's the molarity of the acid in your stomach. Now let's compare that to this. Let's go up here and let's look at milk, which is about pH 6. Bringing this up, the molarity of the hydronium ion in milk is 10 to the negative 6th. But writing that out, it's 0.000001 molar. Now you should see why the smaller numbers are stronger acids. Guys, these pHs are negative exponents for molarities, and as a result, the smaller the number, the fewer decimal places, and the stronger the acid by concentration. So let's move that all the way down the row. And let's take a look at pH 12, which is household ammonia. What does that mean that it's pH 12? Well, carrying that up, that's 10 to the negative 12th, the molarity. Written out, it's this. Guys, look at how small the concentration is of the ammonia, the base of hydronium ion. So what is this all about? Well, guys, if you look, 1, 2, 3, 4, 5, 6, 1, this is the molarity of hydronium ion in water. It's pH 7. So its hydronium ion concentration is 10 to the negative 7th. Anything smaller than that has less hydronium ion than water, and so we call it a base instead of an acid. Now, guys, this then leads us to an interesting idea. We understand now that we can talk about hydronium ion and we can talk about pH. But obviously, we've seen that there's a relationship, and that relationship between these two is linked by an equation. And we're going to write this down. pH is equal to the negative log of H3O plus. But guys, notice the H3O plus is in brackets. This means molarity. The brackets mean concentration. Okay. This is how we're going to finish the day. You should have your, you should have your calculators. We are going to learn to solve for pH when we're given hydronium ion concentration and solve for hydronium ion concentration when we're given pH. So turning to the last couple pages that we've got in your notes, and let's take a look. I'm going to have to click over here and it's going to jump out, but we're okay. All right, here we go. So now guys, looking here, without even writing anything down, think about this. What is the pH of a solution that has a hydronium ion concentration of 1 × 10⁻⁴? Guys, without doing any math, you should understand that that's pH 4. If you don't, you need to revisit this idea of what pH actually represents. But now we're going to make it trickier. What if the concentration is 3.6 × 10⁻⁴ molar? Now understand, when it was 1 × 10⁻⁴, the pH was 4. But now the pH is no longer 4 because this is no longer a 1. So now we know it'll be close to 4, but now we've got to be able to figure out what it actually is. So how do we do that? And the answer is we need an equation. Remember, you will not memorize equations in this class, but you will write them down. So playing along with me in your notes, pH is equal to negative log of H3O plus. Then setting up the equation, we plug in the molarity, 3.6 × 10⁻⁴. And then guys, let me just give you the answer. The answer is 3.4. You now have 60 seconds to figure out how to get your calculator to solve this equation to give you the number 3.4. If you can't get your calculator to do that in now the next 45 seconds, you need to figure out how to run your calculator. I can try to help, but not now, and we're not going to spend the time as a class to get everybody using their calculators properly. Together, we're going to move on. So if you can't get 3.4 from this calculation, put a star by it, put a reminder, hey, learn how to use my calculator. But when you do this properly, you'll find that the answer is 3.4. Okay, so guys, again, if you haven't got that figured out, you're going to need to just let it go for now, because if you don't, you're going to miss how to do the next calculation while you're trying to figure out your calculator. Let it go. You'll have time to figure this out. So now we're going to answer a different question. It says, what is the hydronium ion concentration? You've got this on the last slide in your notes. What is the hydronium ion concentration with the solution of pH 8? Don't do any math. The answer is simply 1 × 10⁻⁸. Again, if you understand pH and what it actually represents, you should have made that connection. But now what about this? What if the pH is 8.12? Well, guys, interestingly, the answer is it's just 10 to the 8.12, but we need to put that in equation form. So let's try to do that now. And guys, please do not write, it's not going to go. Hold on. Let me clean this up. Don't write down the equation until we restructure it. So guys, we have this equation. But now what we want to do is we want to solve this for hydronium ion concentration. So to do that, we restructure it. This is the one you want to write down. It'll be on the test as well. Hydronium ion concentration is equal to 10 to the negative pH. Then we plug in 8.12, again, negative 8.12. And then, guys, doing the math, you should get 7.59 × 10 to the negative 9th. Give you about 30 seconds to get there. And then at that point, If you don't get there, again, you've got work to do with your calculator. Okay, so guys, as you're wrapping up that final calculation, again, if you didn't get it, get help. What I'd like to do is I'd like to wrap up the day by turning your attention to the homework packet. Grab your homework packets, assignment number 1, and let's talk. So guys, stepping through the homework packet and looking specifically at number 1. What are 4 properties of acids and bases? Guys, there are hundreds. So you've got some answers in your notes, but I actually, in the answers to the homework, gave you things maybe you didn't know. There's a bunch of different answers. You pick the ones that seem most interesting to you. Then guys, number 3 is fine, 4 is great, 3 is good, 4 you should know. Number 5, I would underline the words dissociation and ionization, and then make a note to yourself that simply what that means is to break apart. That's all those terms mean, is to break apart. And then guys, turning to the back, 6 is good, and 6 relates to number 5. Number 7 is all about acid and base, hydrogen ion, proton, acceptors and donors, leading back to the Bronsted-Lowry definition. Then guys, looking down at numbers 9 and 10. On these, you're figuring out the conjugate bases for the acids, and then 10, the conjugate acids for the bases. Next to 9 and 10, I would encourage you to write down charges. Be careful of charges. When acids lose hydrogens, protons, hydrogen ions, their charges go down. When bases pick up protons, hydrogen ions, their charges go up. Then flipping over again, number 11 is just like what we've been doing on the screen. Number 12 talks about amphoteric. And then guys, numbers 13 and 14 are all about solving these things where you're figuring out hydronium ion concentration or pH. So guys, what we're going to do on 13 and 14 is we're only going to do the second and fourth columns. So we're going to do B and F, D and H in each set. So B and F, D and H in each set. So guys, the remainder of the time is for you to work well on the homework that you have in front of you. The answers are posted up on the wall. I'm certainly available to answer questions if you need, unless you're watching this at home. And guys, the remainder of the time is yours to get this homework done. Please ask questions as you need, and we will take a look at this next time.